Welcome back to our Chem 152 video series. In this video, we'll talk about how to calculate the change in entropy for various systems. The first question asks us, without using values from our reference table, predict whether the entropy change for these reactions will be either negative or positive. We can think of entropy as the amount of disorder in a system. To try to speculate about what the change in entropy for a reaction might be, the first thing we need to look at is the states of matter that are in play. Now, of our states of matter, solid is the least disorderly and therefore will be the lowest entropy, followed by liquid and then gas. So in our first reaction, we notice that we begin with solid state, and that's low entropy. This is because solids are very orderly compounds. The solid changes to liquid, which has middle amount of entropy. So we've started from low entropy and gone to higher entropy than what we started with. So since our entropy is increasing, we say that the sign of entropy, or as we represent it, delta S, will be positive. For cases like the second equation, which are a little bit less clear, we can look at the number of moles of gas, because gas is the least orderly and most disorderly state of matter. Because it is the most disorderly state of matter, it will have the highest entropy. So for more complicated equations, we can look at the number of moles of gas in order to make a speculation. On the left side of this equation, notice that both of our compounds are gases. We have 1 mole of CH4, 2 moles of O2, and all of them are gas, so we'll write that we have 3 moles of gas. On the right side, notice that we have 1 mole of gas from the CO2, and then water is a liquid, so we will only have 1 mole of gas on the right. So we are starting with a high number of moles of gas and changing to a lower number of moles of gas. So we're going from high down to low. Since we are losing gas, we are also losing entropy. Since our entropy is going down, we say that delta S is negative. So based on these principles, you can make a speculation on a number of different reactions if you don't have the numbers available. In this question, we do have the numbers available, and we can get an exact answer for our change in entropy for this reaction. The reaction we are given is 2FeO solid yields 2Fe solid plus O2 gas. To try to calculate the entropy change, let's organize these items in a table. We'll write the reactants and the products. Now in our table, we are going to write the coefficient in the first column, and then we are going to write the standard entropy, represented with the S with the degrees symbol on it, in the second column. In the third column, we multiply those two numbers. If we look at our equation, FeO solid has a coefficient of 2, Fe solid also a coefficient of 2, O2 has a coefficient of 1. One more thing, when you set up this table, all reactants will be given a negative coefficient and all products will be given a positive coefficient. Therefore, the FeO solid, we'll say the coefficient for that is negative 2, since we'll be consuming it in the course of this reaction. Fe solid and O2 will both get positive signs on their coefficient. Now we go to the table on the right and look up the entropy values, but when we look them up, we must be careful to select the correct state. Now, we have FeO solid as our first item. FeO solid has an entropy value of 60.75 joules per Kelvin mole. For Fe solid, you might notice there are 2 items in the list that say Fe, but we are looking specifically for Fe solid because the state we go for in the table must match the reaction. Therefore, our entropy here is 27.3. For O2, we also look up the entropy in the lower right corner of this table, and we get 205.2. Now we multiply straight across and get our answers for each row. For the first row, we'll get an answer of negative 120.5. For the second row, we'll get an answer of positive 54.6. And for the third row, we'll get an answer of 205.2. Now we'll take all 3 of these numbers and add them together. We get a total of 139.3 joules per mole Kelvin. So every time we run this reaction above, our entropy will change by positive 139.3 joules per mole Kelvin. This seems to correspond to what we looked at earlier with the number of moles of gas. Notice on the left side of this reaction we have no moles of gas because everything is solid. However, if we look to the right, we see 1 mole of O2, which is a gas. So we're going from no moles of gas to 1 mole of gas. And so our moles of gas has increased from 0 to 1, indicating that this should have a positive change in entropy. Our answer of positive 139.3 agrees with those findings. Thank you for watching, and we'll see you again soon.